So it's my great pleasure to introduce to you Salim Roukos, who is a senior manager of multilingual NLP and the CTO of translation technologies at the IBM Watson Research Center. So of course he's very well known for all his work on speech processing, statistical approaches to speech processing, but also to statistical parsing, statistical machine translation and information extraction, and a lot of other subjects he has worked on. Just to mention a few of the highlights, he's co-responsible for the BLEU evaluation method in statistical machine translation, and he has developed the first Arabic English machine translation product ever. And that's just mentioning too. You should have a look at Google Scholar to see the impressive number of citations and the impressive number of papers that he has managed to do on top of his work at IBM, or during his work at IBM. So I think we are very fortunate today that we have him as an invited speaker, because he will be able to tell us about the history, the long history of 3 decades at IBM of work on statistical methods in natural language processing. So we'll give an historical dimension, an historical perspective, and on top of that he will also mention the more innovative new things that are being developed regarding cognitive systems at IBM. So please welcome our first keynote speaker, Salim Roukos.
Thanks very much for the nice introduction. I also would like to thank the program committee for inviting me to come to Doha. I'm originally Lebanese, so it's really interesting to come here and see a significant interest in investing in research. So that's very exciting. So the work I'm going to talk about is obviously not my work. It's the work of me with others. You know, I probably worked with 30, 50 different researchers over the years. So it's a large group of people who have worked at IBM Research and previously at BBN, where the focus has been on speech processing and natural language processing. So IBM, I want to start with some PR. IBM at the beginning of this year announced a new division, something they do every decade or more. So it's a major decision on IBM's part to invest in what's called the Watson Group, a new division, focused on cognitive systems. And this is great for us because NLP is one of the key areas that's a focus for the Watson Group division. And they just announced, they opened actually their headquarters for the Watson Group in Silicon Alley in New York City just 2 weeks ago. So it's an exciting place. Now, we all know, I mean, this community obviously has focused a lot on natural language understanding, but it's always good to see some examples how ambiguous language can be. Noses that run and feet that smell. Ship by truck and send cargo by ship. How can a slim chance and a fat chance be the same while a wise man and a wise guy are opposites? So the reason I'm mentioning these examples is we have to develop methods to decide whether 2 things mean the same thing or different things or completely unrelated. And it's a very rich thing with language. It's a very long and challenging thing. I've been working on this for over 25 years, and we are still inching up. We're making progress, but it is really a long marathon, or 10. So the classic problem is you want to extract information from unstructured text. So if you have a structured database, you could discover, for example, who runs companies. So Jack Welch runs GE. But our goal is to find that same relation between 2 arguments using unstructured text. Now, this particular example is very hard. If leadership is an art, then surely Jack Welch has proved himself a master painter during his tenure at GE. It's going to be a while before we figure this one out. But nevertheless, there are hints in here that actually make it not so hard, maybe. So when we are dealing with complex question-answering systems, keyword matching is not sufficient. So let's take an example. If the question is, in May 1898, Portugal celebrated the 400th anniversary of this explorer's arrival in India, this is a Jeopardy-style question. And if the piece of text that you're looking at is, in May, Gary arrived in India after he celebrated his anniversary in Portugal, then you may decide, if you do just keyword matching, that celebrated match, that May 1898 matches in May, it's 66% match, maybe higher if you do IDF. Anniversary and 400th anniversary, close enough. Portugal, close enough. And India, India. So you might draw the conclusion that Gary is the answer to the question. But as you know, this is not good enough. What you need is a fancier way of matching. So if the sentence snippet that you're scoring now is different, on the 27th of May, 1498, Vasco da Gama landed in Kapad Beach, then you have to figure out what's a date and do the matching to see if they match. So 400th anniversary and May 1898 computes certain quantities that you can perhaps match on the right-hand side. The same is in the arrival in being similar, have the same meaning, or a paraphrase of landed in. And the third one is a geo database, knowledge base, where Kapad Beach is located in India. Now, in the actual Watson system, there is over 100 kind of what we call scorers, things that use various knowledge bases, models to decide if things are related. And that's sort of really the big thing that I think going forward we'll have to do much more in, which is marrying NLP techniques with knowledge base extraction techniques so that you can start reasoning and figuring out what makes sense to infer in complex situations. So I'm not going to talk a lot about that today, but I wanted to give a hint of what's going on going forward from a Watson Division Group focus. So IBM started a new term. Oh, I forgot to say that the answer is this one. And actually, this turns out to be what the system finds in this case. So IBM started defining the term cognitive systems. It's a new term for us. We've been about maybe 2 years now organizing our research effort and our development effort around the cognitive systems. And the definition, is always tricky with these definitions. So I will read it. Applying human-like characteristics to conveying and manipulating ideas that when combined with the inherent strength of digital computing can help users address problems with higher accuracy, more resilience, and on a massive scale over very large bodies of information. Now, as a famous physicist once said, that the best way to teach, actually the only way to teach, is to give an example. So I'm going to give Watson as an example of a cognitive system. So it teases apart human language. It's clearly in a particular domain, and it can demonstrate human-like accuracy in that narrower domain. And obviously, computer-based, it will be faster and can handle larger quantities. So now I'm going to sort of talk about 4 topics. The first one is information extraction, then machine translation, then speech-to-speech translation, and finally I'm going to talk about an application of machine translation, where we assist humans produce human translations. In information extraction, the idea is to find named mentions of entities of interest. So American Medical Association is a named mention of an organization. Air is a nominal mention of a person. And its is a pronominal mention of an organization. And the goal is to find all the mentions in a document and then do co-reference resolution, meaning group the mentions that correspond to the same entity in the document. So all the green mentions correspond to AMA. All the red mentions co-reference to the same entity, Thomas Reardon, so that when you see a piece of text, chairman of its board, we can extract the relation that Reardon is the chairman of the AMA. We have been working on this problem for a number of years. We've developed a toolkit, and we've developed many domains. So I just want to show you one domain for news, where there are 50 different entity types, and anything that's like, for example, green with a dark black font, like Robin Cook, is a person. So the color coding is telling you the type of this piece of text. The relationships are shown below here. So the second relation is Robin Cook is a citizen of Britain. So that's extracted from this context here, Foreign Secretary Robin Cook of Britain. Now, clearly, these are statistical estimates from a local piece of text, so it's not going to be very reliable in terms of its true accuracy. This is where the marrying of text extraction with knowledge bases becomes very important, because if you see the same evidence over many pieces of text, then you can believe the fact stronger. Now, as you might expect, we have built these systems using statistical models, so the key is to find examples of annotations of the domain that you want. Our focus is on adaptation, so we develop toolkits to help you annotate data quickly and help you build these systems that do mention detection, co-reference resolution, and relation extraction. So the same domain can be done in Chinese or can be done in Arabic. And here I'm showing the web-based tool for annotation. You click on words or characters and annotate them with the type on the right-hand side. Or you click on two mentions and pick a relation from the left-hand side. It's an available service, and I will give you some pointers at the end of the talk where you can get to see it and play with it. And essentially, when you deploy such a system, what we have found, it's important to keep it up to date. So after you've deployed the system, you actually want to keep sampling the output and correcting it by humans so that the system is kept up to date with the drift of the language to keep the performance at an acceptable level. So quickly, just to show you what goes into that system, if we have a piece of text like this news article, the first thing we do is we find the words, which means separate the commas in English. In other languages, it's other things, such as segmentation in Chinese. Then we do sentence segmentation, find the units that correspond to a sentence-like unit. Then we do case restoration, because sometimes the text may come not in the appropriate case for languages where that matters. Then we do parsing, and I'm going to talk some more about parsing. And then semantic role labeling, who did what to whom. And then we do mention detection of the types I just mentioned earlier. And then co-reference resolution. So maker is the same as Abbott Laboratories, is the same as its in this particular snippet of text. So all these mentions correspond to the same entity within the document. Then we do relation detection. So Abbott Laboratories made an event communication, and you sort of read the next thing. And Abbott is located in Illinois. And then time is very important also. So we do quite a bit of time processing, finding intervals and dates and timestamps. So for example, a year ago, we were able to resolve it to 2007 because we know the date of the article, and so on. Sometimes the granularity can be a day, a month, a year. So the thing I wanted to focus on here is parsing. I'm not telling you all the algorithms that go into building such a system, but parsing is a core component in many of the components. Because if you get the sentence structure, it helps you infer relationships. So I want to mention some results and some challenges that we have to deal with statistical parsing. Some of you may know statistical parsing was started by us in the early 90s. And so it's been about 20 years, 22 years actually, to be precise. And surprisingly, in spite of the fact we think we made a lot of progress, we still are having challenges. So let me explain what I mean by that. So Ontonotes is a particular tree bank that the LDC has released, and it contains Wall Street Journal and other sources of data, Newswire and weblogs and other variety of data. And if you run a parser trained on Ontonotes on Wall Street Journal test material, you get about 90%. This is state-of-the-art parser F measure. If you run on a Ontonotes test set, it's a little bit more difficult. The performance drops to 89%. But now, if you look at the coordinated structures, so instead of computing an F measure over all the non-terminals, you just focus on the coordinated structures, finding A and B, or A or B or C, then the performance drops to 80%. And that number is really not that much better than our early results. We used to be in the low 70s, mid 70s, 22 years ago. So we still have a long ways to go on capturing coordinated conjunctions. And I wanted to show some examples of that. Actually, I think I have it. Sorry, I should have prepared more carefully. Here it is. So this is an example of the truth is the tree on the left. So you can see here that the joint POW-MIA accounting command or JPAG. So that's very easy for us to figure out what the conjuncts are. But the parser gets confused, and this is state-of-the-art parser, and it discovers that it is command or JPAG. It gets confused by the accounting. Remember, it doesn't know enough semantics, right? So that it's like a reasonable error, so to speak. But nevertheless, it's very silly from an understanding point of view. So this is an example. Clearly, this example is picked because this is a file which contains all the errors. So, you know, but just to show you some examples. So what I wanted to do is show you in action a sentence that came up actually only last week, and I was talking with somebody. So the first thing is I cut and paste an article from the newspaper Al Ahram last night, and if I should make this probably smaller, this way I can run the information extraction system on this article. Oops, okay, it's a little slow. So what you can see here is that the entities I mentioned to you, we can see, for example, that Abdel Fattah al-Sisi is the same as president, the same as all the yellow mentions are highlighted when I go on this entity. So al-Sisi below and his condolences here, it's the same co-reference of all the mentions of this person. We also can see some relations. So he is a participant in an event, and the event is, it's hard to see, it's the funeral. It's, you know, it's what gets highlighted, okay? So we can find actually quite long distance relationships at about 70% F measure, and it relies obviously on parsing, but unfortunately we sometimes make horrible errors because of the parsing structure. So what I wanted to show you is the one example sentence I was processing a couple of weeks ago, and it's a technical article I was processing. And this is the sentence, so let me run the extraction on it and display the parse for you. And I will read the parse as the sentence as we look at the parse. So don't suffer too much about looking at the tree for now. A correlate is an abstraction of a network of neurosynaptic cores that encapsulates all intra-network connectivity and all intra-core physiology, and only explores, and this is where the mess happens, external inputs to and external outputs from the network. So the conjunction is external inputs, external outputs from the network, whereas the parse is completely confused. And if you make such big errors, it's very hard to find relationships accurately. And also, it's a generic problem. Our machine translation relies heavily on parsing also. It affects parsing in a significant way. When we look at errors, typically we find the parser as being one reason why it contributes to the error. Oops. So I'm hoping we can get more people interested on working on conjunction and just using as a metric F measure on conjunctions, instead of focusing on the overall F measure, which I think is probably misleading because you can make small improvements, but they don't really change the fundamental nature of the big structures. Okay. Now I'm going to talk about machine translation. So clearly there are many applications. Text to text, where you take a source language, translate into a target language. Speech to text, you take speech, do speech recognition in the source language, and then translate into text in the target language. And finally, speech to speech. If you synthesize the output of the text translation, then you can speak with another person. If you have two systems for each of the ways, you can do speech to speech communication. As you know, we started with statistical machine translation also in the early 90s, late 80s, early 90s. And the most important feature of machine translation, statistical methods, is not only do you get the ability to build high-quality systems, you get the ability to tune or adapt to new domains. And that's really very important going forward. If you have a particular subdomain you want to do machine translation in, you can benefit a lot by using the data to customize the machine translation and get a boost in accuracy, as opposed to a general system. So I always like to show this slide. This shows our progress over the years, because it's one of those things where it really has been a steady progress every year. So this shows that in March 2002, we started working as part of the DARPA TIDES program on Arabic to English, and these are blue scores, higher is better. And you can see there are different test sets. The red curve is one test set, the blue curve is another test set. But basically, you see there is progress going on every year. And I remember when I used to give those talks, people would tell me, oh, but maybe it's going to saturate. And looking another 5 years later, from 2006 to 2010, now the metric changed. It's the human translation error rate, which means take the output of the machine, ask a human to correct it till it's correct, measure the edit error rate, the number of edits, percentage. And if you look at the red curve, which is Arabic Newswire, it came down from about 17% to about 7%. And the green curve is Arabic weblogs, so they're harder, and the error rate dropped from about 32 to about 15%. So the key, though, is that progress is happening at a reasonable rate. And more recently, over the last 3 years, I'm showing results now on Chinese. And this is part of a new program, current program called DARPA Bolt. And the metric is an automatic metric, which is just the average of TER and blue. So lower is better in this case. And you can see, again, that we are still making progress, at a reasonable rate. It's not saturating. And I think this is really important because I actually saw it in action. I still remember when we used to give demos of machine translation, and once in a while the sentence was correct, whereas now I'm going to give you a demo and show you that it's more frequently than not that it's correct, at least for some languages like Arabic to English. So to give you a little bit of a flavor on the machine translation that we use for Arabic to English, it's a large statistical model. It's a maximum entropy model. And what you do is, given that you've translated some fraction of the input source, you compute the probability of where is the next source position you want to translate. That's the jump J. And what should its target translation be? That's the word W. And you use, obviously, the history is everything you've done so far, including the analysis of the full source sentence, such as parse tree and other things that you may have. And you train such a model to, maximum entropy is the same as maximum likelihood with exponential models. And I think the most important feature is that you can throw at it as many features as you can. So I want to show you an example of a feature that we've added that makes it quite a big difference for a certain set of problems. So this is the output of a machine translation system where the Arabic is going top to bottom. The parse tree is on the left. It's hard to, you have to get used to reading it, but I think, you can see the alignment of what's produced on the English side. And the common problem you see today with many Arabic to English machine translation systems, because Arabic is verb, subject, or object, starts with a verb, that the English will typically have a subject pronoun that's not really correct. So the system here said he visited a number of bakery owners. Whereas if you analyze the parser, the parser really knows there is a subject. My animation is not working. Here it is. So the parser knows that there is an NP subject. So if you have a feature that says, when you compute the probability of the next jump, is the subject covered, meaning that all the subject phrase has been translated, that feature can affect that you should not translate the verb till you finish the subject. And it's a statistical thing, there are no guarantees, it's all about scoring things. But you can, giving the data the chance to learn the power of such a feature if it turns out to be useful. And it is useful, and in this case, it produces sentences more frequently than not that where the verb is moved. So the subject, a number of bakery owners, is translated first, then the visited is translated to produce a more fluent English sentence. Sometimes in Arabic, these things can be quite long, so maybe 15 words into the sentence. So it takes quite a bit of structure, and it also takes more accurate parsing. Because if the parser is not doing very well, then you're not going to get the benefit of that feature. That's why it doesn't work all the time. Now, we still have problems, obviously. So sometimes we drop content, like here. It should be the area supply managers. It became just the supply managers. All right, so this system, we evaluated it recently in May, August 2014. And we compared it on Newswire text. And we compared it to an online system called Online A. And we asked a judgment on a 6-point scale from 0 to 5. And you can see that this system that I just described at a very high level is better than the Online A systems. And it's true for both Arabic and Chinese. Now, the Chinese system is actually a different system. I'm not going to describe it here, but if you look at the papers that we have, you can go find the details. We have lots of papers on the subject. But that's actually, this is quite a difference, of about 0.3 on this human scale. Every 0.1 is roughly 1 to 1.5 blue point, just as a rule of thumb. These things are not highly accurate, right? Depends on lots of details, what works, what doesn't work. But as a general rule, I would say each 0.1 in the human eval is about 1.5 blue points, or more precisely, ter minus blue. So let me show you an example, just to illustrate. So if we look at the second sentence here, the online system said called the National Alliance, whereas if you look at the DTM system from IBM, the National Alliance to Support Legitimacy, supportive of the Muslim Brotherhood group, so this was the name of the organization, right? In Egypt, called on his supporters. It should be on their supporters, right? So actually, I used to say to the group, we shouldn't worry about pronouns. Now we are ready to work on pronouns, because before we did not even get the words in the right order, so it was premature to try to have this more refined model. So I would say now it's probably key for us to get our pronouns correctly connected, and that's where the information extraction stuff can come into play. Surprisingly, up to about a year ago, information extraction was not helpful to machine translation, in spite of many things we have tried. But I'm still an optimist, so we'll get there. Another example is at the bottom. There is the red stuff. Head of bayonet in Marsa after the overthrow of massive popular protests versus the spearhead in ousting Morsi after mass protests. So it's much more fluent. And the Morsi is one of those tricky names. It means many different things. So getting the name translation also is another subtle issue. So I wanted to show you a demo of the system. So when I click on this green button, we're going to go get a web page from the Arabic BBC news site. When it becomes black, it got the page. So it got the page, and it translated it now. So we can read a few of the titles. Tunisians elect their parliament amid security alert. Not bad. It typically is better in the body of the text, actually. But let me read some more titles. Lebanon, 6 soldiers killed in clashes with gunmen in Tripoli. The start of early legislative elections in Ukraine. Real Madrid defeated Barcelona 3-1 in El Clasico. It's pretty good for a machine. This is actually, I know for a fact, it's the best machine translation for Arabic English. Okay? And as I said, the body of the text typically. Now, I got lucky today. Typically, I have a problem when I give this demo, so there's at least one bad error. But hey, I'll take it. So over the last 2.5 years, we've been working on the DARPA BOLT program, which is focusing on much more informal content. So I sort of showed you Newswire translation. So discussion forums, chat, text messages, and this is focused on simplified Chinese and Egyptian Arabic dialect, because once you get to informal, people will speak in the Arab world in their own dialect, and there are lots of dialects in the Middle East. So contrary to, or in contrast to the GALE program, it's the same metric, it's still human translation error rate, and I think the most important difference is the dialectical aspect of the Egyptian Arabic. It's a whole new language, really. It's actually quite challenging to make it, it's quite different from Arabic, let's just say it that way. One advantage of informal is they tend to be shorter. Whereas in Arabic, they tend to write in paragraphs when it's an article, so it's more like 50 words per sentence. But here it's much shorter, but because it is so informal, it's much harder to translate. We have compared our system also to the online A system. And in this case, I think it's an unfair advantage we have because we have training data, so we don't run this test anymore. You know, this was run in November 2012. We're much better than the online system because we know the dialect much better than they do, let's say. And the same is true for Chinese. Chinese also, when it's on their weblog discussion forum websites, they tend to be much more informal and more flexible with the use of the language. So targeting that data, this is the customization argument I was making earlier. So being able to train on that kind of data makes a difference in the performance of the system. Notice that the Arabic system scores lower than the Chinese system. It's very hard, I have found, to trust human judgments about the quality of machine translation when the language is different. So I don't compare these numbers anymore across languages. It just does not make as much sense because different cultures, people speaking a language have different tolerances for certain errors and their scales are not comparable. So I don't compare across languages. We've started a year ago actually, working on chat, and this is an interesting problem for this region here. So this is an example of an actual chat, and in chat in Arabic they use a Romanized keyboard, you know, of the smartphone or regular phone actually, and they type it in Romanized letters, and they have the numbers to capture some of the consonants in Arabic that are not available in the Romanized keyboard. So you see numbers like 2, 3, 5, and 7. And what I'm showing on the right is the translation in Egyptian orthography. Now remember, this is a spoken language, so each user spells the words according to their concept of what the right phonetic structure of the word is. So there's a lot of variability in the spelling of the words when they're written in Arabic, but in Romanized letters. But they also mix with it some English. So you can see, till now, there's a typo, NW. And then further down, told him, it actually is they told him, so the reference translation is incorrect here. This is human-produced reference. And if he wants. So this is really a very challenging problem. First, you have to deal with the spoken language with non-standard orthography. You have to deal with all the prefixes and suffixes attached due to the dialect to the spoken word, or to the English word or French word, depending on which dialect you're talking about. So it's actually quite a challenging problem, and it's going to push us in terms of handling diagnostic, it's called, languages, and actually it's a little bit more than that. It's really 3 languages together. Now, in terms of our work at IBM, we have deployed machine translation inside IBM for IBMers to translate their documents. We've deployed systems for customers in the patent domain, Chinese, Korean, Spanish, Brazilian, Portuguese. And we have done some work on the use of machine translation for human post-editing. I'm going to talk about the last one a little later. And the system is called Enfluent, and it supports a translation from a variety of devices, includes crowdsourcing. You know, IBMers who use the system can correct, and the system learns from these corrections. Actually, some of our systems are updated on a daily basis. So the system is continuously learning new things. We have about 30 language pairs. And these are screenshots of some of the interfaces, cut and paste, browse, trans-browse that I showed you. It's the same time multilingual chat, you know, different people can speak in their own language to communicate, and mobile devices. So now I'm going to go to topic number 3. I want to talk about speech-to-speech translation. I want to this is current work, is also sponsored by DARPA. And as I said earlier, to do a speech-to-speech system, you have to have a full system in one direction and another system in the other direction to support a two-way conversation. Now, the new thing is, if you build a system, there will be a lot of words that are out of vocabulary to the system, or there may be errors in the system. So we have added a dialogue component on either side of the system. So the English speaker talks to the English system, and the dialogue manager will manage the interaction in English until it's sure of what the English speaker intended to say before it sends the translation to the Arabic speaker. And the same on the other side. There is an Arabic dialogue manager to handle the Arabic speaker in the case of a speech in English to Arabic system. And there is a bunch of commands that allow the user to interact with the system like a typical conversational dialogue systems. Maybe I should just leave it at this high level, but the point is, I would say I want to highlight here that you need to deal with synonyms. If you don't know a word, you have to ask for a synonym. And if you don't know the spelling of a word, in some applications, you may want to figure out how to get the spelling. So there are special components for those kinds of functions. But I want to talk about the detection of OOVs. You know, when somebody says something and they have a word that's not in the vocabulary of the system, how do you find it? And how do you deal with it? So let's say the user said the contractors can do, and the ASR figured out the contracts need do, and the system says, I heard the contracts need do, say replace text or start over, because it was not sure of its recognition. The user may say replace text and say, replace text, contract needs, begin paraphrase, builders can. And now you will get the builders can do. So that's the spirit of the interaction. And we do this through various embedded grammars. Let me skip that for now. And fundamentally, we did 2 evaluations with DARPA, one in 2012, one in 2013, and the 2014 one is coming up in 2 months. And essentially, the word error rate with a Gaussian mixture model for the speech was about 14%. Last year, we switched to convolutional neural network model, and the error rate dropped to 7.5%. The majority of the reduction in error is due to the convolutional neural net model. So that actually was a great progress from a speech recognition point of view. We also improve our models for spelling, the commands, and for the cache. The cache meaning the system knows what it said. This way, when they say replace text, it knows what words to look for if they're trying to correct a word. So let me talk about OOV detection, because that's perhaps interesting and new. And actually, it's an important theme. It's not enough to have high accuracy systems. You need to have some notion of confidence in the system's output, because the confidence in the system outputs allows you to do things downstream in applications. So there's a lot of work that we've been doing on confidence estimation, and I'm going to talk about that a little bit later. So if the person said, but to survey it aerially, that's an OOV for the system. When we do the speech decoding, we'll get a confusion network, which means the most probable path plus alternatives. And you can see that for the area of the speech where the speaker said aerially, we discovered Harry, Ali, or Harry, early, or what we call fragments. We have triphones fragments, you know, phonetic engrams to try to fill the space of OOVs. So you can see that the system is actually quite confident that it doesn't know what it's doing in the red area. Okay, so that's how fundamentally we discover OOVs. So there's this notion of metrics, and I'll tell you a little bit more about the features used to detect that region. And then we measure what's the fraction that we found. We have to measure the boundary, because if you found too much speech around the actual OOV, that's not good also. So we talk about false alarm rate. So we try to target 5%. We don't want to produce more than 5% of false alarms in OOV regions. And we want to get the maximum, you know, detection rate possible. I defined that, so I'm going to go quickly. So this is the OOV detection rate versus the false alarm or false positive rate. And you can see at 5%, we are at about 75% detection. So we detect 75% of the OOV events with only 5% extra false alarms. This is done with the Gaussian HMM. This was our system in phase 1. Then we went to phase 2, where we switched to convolutional neural networks. And we also built a richer classifier of the OOV region. So not only do we look at the confusion network, but we also look at additional features based on durations, based on text normalization, and various training data to help train a classifier. And essentially what we show here is at the same 5% rate, we improved from, the green curve is improving to CNN over Gaussian mixture model, the red curve. And the richer classifier moves the green curve to the blue curve, which is about 80%. This is for English, OOV detection. Similar techniques are applied on the Arabic side, but the performance is worse on Arabic, in part due to time. As you all know, it takes a lot of engineering to get these things to work. So now we have a much better Arabic system, but this is from last year. And based on an evaluation by DARPA with 24 users live, the users were very disturbed when they saw false alarms. So you really have to control the false alarm rate. So I wanted to show you an example. So this is an actual dialogue from last year's evaluation of the evaluation. This is a real person trying to do a task with a. So this is the English speaker. I'm going to play it for you here, and you see the transcript or the speech record, to be more precise, in blue.
Good morning. My name is Sergeant Truman. I'm looking for information on a patient named Ashkar.
So you can see Ashkar is ask cow. Okay, so we already have a hint it's in OOV. The system, using its detection
I
says,
am not sure about.
Ashkar.
If it is a name, say it's a name. Otherwise, say begin paraphrase or start over.
So the system found the OOV region pretty well and asked, is it a name? And in this case, it is a name, so the user said it's a name.
It's a name.
And the thing got translated in Arabic for those people. Who speaks Arabic here? Oh, small minority, sorry. Let me just play it because you want to listen to the last word in the Arabic.
صباح الخير، اسمي العريف ترومان. أني دا أدور على معلومات عن المريض. اسم
Ashkar.
Now, I have to admit, Ashkar, Arabic is very rich in the sense that names typically are also nouns. So Ashkar is close to Ashkar, which is what this guy is saying in the next sentence, because he's repeating, And then we translate it into blonde, which is the meaning of the Ashkar name in Arabic. So we still have a ways to go, which is bilingual, name matching, and those kinds of issues. So we'll get there. It's work in progress. There is also some results from NIST earlier this year. This is showing the systems in phase 1. And what they did here is a controlled experiment where they tried one initial utterance and allowed the system to dialogue till it finished, up to 3 tries. And it's measuring the rate of success. So you can see that we are in the 50, used to be in the, let me do the whole animation and then I'll explain. So if you look at the dark brown, this is the average success rate. So in other words, we are in about 50 to 60% of the utterances we handle correctly. These are sentences that have problems, OOVs. They are targeted. This is just to measure how well do you handle OOVs. So we still have a ways to go, but we made quite a bit of progress from last year. And these 4 graphs are showing you the detection rate of errors and then the actual correct translation rate. So if you focus only on the correct translation rate, it's about 60% for IBM. Okay, the last topic I want to talk about, actually there are 2 more topics. I have a small little subtopic at the end, is the use of machine translation for human post-editing. IBM spends quite a bit of money on translating content every year. IBM translates about 400 million words, new words. There is another factor of 6 more that's reused. But there is 400 million new words. And they use 115 translation suppliers. So it's a very distributed organization. And as you may know, translators are basically freelancers. So there is probably 10,000 people freelancing from home working for these agencies. And obviously, IBM focuses on reducing its cost. And they have done a lot of computer-based automation, managing the previous translations, code translation memories, and so on. So they had tried to use machine translation in the early 2000s, and it did not work very well. So they were very reluctant to try it again, because nobody wants, I was going to say a bad word, don't, do something with my business. But eventually, they were willing to try again. And let me just define some concepts. The concept of a fuzzy match is you have a sentence you want to translate, This is from Spanish to English, let's say, Hillary Clinton in Mexico. You might have translated earlier Hillary Clinton in Francia, so you have to change only one word and get the answer. So that's called a fuzzy match. Typically, if it's 75% overlap or more, they typically start from the fuzzy match and post-edit that, changing one word or however many words they have to change. Okay? So, or you could use MT, and in this case, the sentence is so short that MT is really good. So you could actually just accept the MT and not do any editing. So that's one concept. So MT versus fuzzy match. And the other concept is no proposal. Let me skip this because this is too much detail. And this is the UI. It's a standard UI for all IBM vendors. They use the same tool. And essentially, to get high accuracy machine translation, we customize the machine translation system to the specific document we want to translate. So we have a document that has to be translated by humans. We find a subsample from all our training data that's closest to this input document, create that parallel corpus and language model, build a language model, translate the document, and ship that to the humans for translation. So it's a customized at the document level machine translation. And we ran a pilot in 2010, and the pilot was about 16 translators, over 150 different documents shipped, as it's like a little process. I mean, it was part of the business process. And we cannot insert a lot of detail delay. So we had a response time within less than 24 hours. And at the end of the day, this pilot, over a period of, I think, 9 months, with the humans translated about 4.5 million words, which is about a person year of human translation time. So it's a huge pilot. And these are the statistics of, it's about 4.5 million words. 1 million of them were exact matches, which means the human only picks one of the many exact matches, because sometimes the document context for the same sentence, there are different translations. So even exact match requires a human to screen. And then the fuzzy match is 1.5 million. And no proposal is when there is nothing close in the previous memory, so you have to do it from scratch. We call it no proposal. Now, to do our analysis, we give them the folder with the fuzzy match and the machine translation matches. And on purpose, we remove the machine translation in 5 to 10% of the segments. This way we have an A/B comparison on all the folders, so there is no variability in content to affect our statistics about is machine translation presence helpful or unhelpful. So this shows for Spanish, it shows that for 53% of the word, the humans, by their choice, they have to decide what to do, right? So they do what they think is best for them. They used machine translation hypotheses, or choose MT, 53% of the time. So that already is an encouraging sign. At least they think they're faster. We don't know if they're really faster, but they think they're faster. That's a good sign, because I remember when we started, the translators were very skeptical. The humans, they were saying machine translation, even though IBM was pushing to try it, they were still a little reluctant. So this is showing you the statistics now between when there is no MT present, 42% are, even though there is a fuzzy match present, the translators still prefer to start from scratch 58% of the time. So even though the fuzzy match is close, like 75%, but it's a long sentence, it's too complicated, so they just start from scratch. They feel it's much faster for them to type it through. And obviously, when there are no proposals, they have to do it from scratch. That's why the 100% is on the top table. Now, when machine translation is present, when it's a fuzzy match condition, because these typically will be easier sentences. Typically, if it's repeated, it tends to be easier. I have other reasons why I'm saying this, but let's just accept that as a fact. And you can see that in that case, when MT is present, they pick MT 42% of the time. And the MT is helping both with the fuzzy match sentences, it decreased that percentage, and the NP, obviously. So it's helping both sides of the equation, if you will. And in no proposals, 53% are actually MT as opposed to from scratch. They found enough value. So we measured their speed, and if we define the unit time to be the time it takes to produce one word in the no proposal case, if they use a fuzzy match sentence because they're reusing memory, they're 30% faster. But if machine translation is present, you get another 30% speed up for the fuzzy match condition, and 41% for the no proposal condition. So that was really a huge success. I mean, this is actually in production now at IBM for 5 languages: Spanish, Italian, Chinese, Portuguese, and French. I forgot to turn my email off, I'm sorry. And we've been working on a pilot. This is an old slide, so it's not pilot anymore, but it used to be pilot a year ago. In particular, I want to talk about Japanese, because this is showing you utilization rate of machine translation is the blue, for the no proposal for the bottom graph, the fuzzy match for the top graph. But you can see that for Italian, they use about 40% machine translation, and for Japanese, they were using about 30%. They thought it was helpful, but actually they were slower. Okay? Maybe it was easier effort, but it was slower from a speed point of view. And since they are paid by the word, that matters. So English to Japanese was not good enough a year and a half ago. So what we did is we added a confidence metric. So we said, instead of giving them MT all the time, let's tell them our confidence of how good the MT is. And we did this in 3 grade levels: A, very confident, B, and C. And the suggestion was that they should learn what to do with the A's and the B's and the C's. They don't want us to hide it because they still sometimes want to cut and paste an expression, because if it's a difficult expression, MT is very good at getting those technical translations, and they know to go look for it. So you want to always show it. You just are telling them when to spend semantic, cognitive time, human time, to process the sentence to see if you're going to post-edit it. And since I'm running out of time, we built a classifier. And the trick is the classifier has to be also customized to the job. So not only do we have an input document and we find a corpus that's closest to it, we also have a control confidence estimation set that's used to train a system and estimate adaptively the confidence metric for that job. So the confidence classifier is adapted on every job on itself. And fundamentally, the correlation of the adaptive confidence estimation is about 0.53 Pearson versus a 0.1 when you don't do the adaptive stuff. And by improving that correlation for the adaptive confidence estimation, we were able to get speed ups for human translation. Because now, if you look at the last bar graph here, you can see the Japanese with MT, this is NP1, NP0, there's no MT, is a little faster. It's about 10% faster. And in the remaining 1 minute, I'm going to skip this. This is in detail. I want to just tell you that the things I talked about today are available for you to play with. IBM has started something called Bluemix, which is an app development environment. But more specifically, there is something called Watson Developer Cloud. If you type in your search engine, you'll find it. And this allows you to see some of the technologies I talked about. And let me see if I can go there. I think it's here. So this is the website. And in the Developer Cloud, it says it's the place for companies, startups to build applications, cognitive applications. It comes with a bunch of services, and you can add your own services to build your own cognitive applications. And if we look at, and there is quite a bit of material to help you learn how to build these apps. And in particular, we can look at some of the available services. This was also announced when they opened the headquarters. It was part of that same announcement. And you can see here some of the services: concept expansion, language ID, machine translation I talked about today, message resonance, which basically says, change the word from this word to that word if you want to address this community of people. So there is a statistical model that helps you pick different terms from your original message. And question and answer APIs, and relationship extraction, which is the information extraction I mentioned to you. So you can go there as a beta user. You can get free 30-day trial. I think you can play with it and see things. And that's it, I think. And a bunch of services.
Thank you very much. There's time for a few questions.
Salim, thank you very much for an exciting talk. I agree with your idea that we should be doing expert evaluations on particular construction, particular coordination. introduction to the study at that time with the Stanford group and with Joachim Lieber's group and itself. And we did look at coordination, so thank you. You might find...
Yeah, I'll check it. Are you better than 80%?
Sorry?
Are you better than 80%?
It depends on the construction.
Okay.
So the problem with the attachment problem that you mentioned is the model rather than the grammar, so we're not that good.
Yes. And as I said, they appear to be esoteric and small in numbers, but when you screw it up, it screws up the system in such a big way that it's really unacceptable error. If we had a weighting of the errors by some notion of severity of applications, you will discover these things are really, really important.
More questions?
Thank you. Good talk. In the beginning of the talk, you referred to blending the NLP or information extraction with the knowledge bases. And right now, there's Google and Microsoft have knowledge bases and free base to some extent. How do you think the community should address this?
They should use whatever they can get their hands on, but I think the real challenge is to figure out how to extract reliable information from lots of real text. I think Freebase is very special, I think the trick is to figure out ways for automatically learning these things and accumulating the knowledge. Because as I always used to say, when we shipped systems in the old days, they were stale by the time we shipped them because they're not learning continuously. And I said earlier, our machine translation learns new words and phrases on a daily basis. It's really key to get the quality.
Thank you.
I think the challenge is also, it's a big project. So for researchers, you have to work with somebody, Yeah.
One last question.
Thank you for an exciting talk. So there has been all these big data projects, you mentioned them, and then you also showed that actually in your setting in IBM, for example, the post-editing actually, is a business case. Right, so my question is essentially from your perspective, is the landscape shifting that now actually companies see that speech recognition, machine translation, other NLP technologies actually make money? And if yes, does this change how the researchers actually should work?
Yeah, I guess that's the underlying assumption of my title. Clearly, many companies, IBM included, are betting on cognitive computing kind of systems. I'm a realist. I've been doing this for a while, so there will be some disappointments. But I think judiciously picked applications are probably good enough to maintain a momentum in that field. So I'm actually very optimistic about industry investing significantly into effective research ideas. So it has to work, It's not enough for it to be elegant. It really has to work robustly and with some confidence. And I think everybody who works in the business world, let's say, I was going to say the real world, you have to worry about those issues. As I say, there are lots of elegant ideas we have invented, actually, at IBM. We do not use them. They do not work.
Thank you very much for a great
Thank
talk.
you.